Next, let's look at the binary search algorithm, which is very related to sorting. And that's because binary search can only run on an input that is already in some type of sorted order. Because binary search is sort of an algorithm that you might already know intuitively. If you're searching for something, in the worst case, you would have to look at every single value in the input to find what you're looking for. And let's say you were looking for an 8. In this example, you wouldn't reach that until the last position. So you would have to look through all of these before you realized, well, the 8 was at the end. Now, only if you knew that the input was actually in sorted order, you could have done it more efficiently. And the idea is the same with dictionaries. When we have a really massive list of words, we put them in alphabetical order in a dictionary. So if you're looking for the word banana in the dictionary, let's say you go at the halfway point of the dictionary and we find words starting with the character J. At that point, where would we go? Would we go to the second half of the dictionary or the first half of the dictionary? Well, we know the character B starts before the character J, so then we would go to the first half of the dictionary and then look somewhere over there. The idea is the exact same behind binary search. Another example, if I told you to guess a number between 1 and 100, and I told you if you guess wrong, I'll tell you if your guess was too small or too big, of course what you would do is guess 50. So then if I tell you your guess is too small, then you know that the answer is somewhere between 50 and 100. But if I tell you your guess is too big, then you know the answer is between 1 and 49. Or the third case is your first guess was already correct. The good thing about this guess is you can eliminate half of the possibilities and reduce your search space. And you can't only do it once, you can repeat this operation. So if I told you your guess is too big and the real answer is between 1 and 49, what would you guess? Would you guess 2? No, you wouldn't guess 2. Because there's two possibilities. I tell you that your guess is too big. That's the good case, because if 2 is too big, then that means the only answer left is 1, so you found the answer. But what if I tell you your guess is too small? Then the answer is somewhere between 3 and 49. You didn't really narrow down much. You only narrowed down like 2 values. So that's why we guessed the halfway point. It's less risky, because we know every single time we're going to eliminate at least half of the possibilities. So in this case, we would guess something like 25. And maybe I tell you your guess is again too big, so then we know that the real answer is somewhere between 1 and 24. We narrowed down half of the possibilities again. This is the idea behind binary search. Now, it's most common to run binary search on some input, usually an array. And it's very important for the input to be in sorted order, because if it's not in sorted order, then we can't run binary search. Because if it's not in sorted order, then the best we can do is just individually look at every single element, and we know the time complexity for that is big O of n. But binary search is going to be even more efficient. Let's continue. So in this example, our target is 8. We want to return the index that the value 8 appears in the array. And if the target doesn't exist in the input, and that's definitely a possibility sometimes, what we normally do is just return something like -1 to indicate, -1 isn't a valid index, so that indicates that we weren't able to find a solution. So what we would want to do is go somewhere close to the middle of our search space. In this case, we could either go here or here, but what's the main algorithm that we use? Well, first we want to have our boundaries. Our boundaries tell us what is the portion of the array that we're currently considering. At the beginning, the value 8, the target, could be anywhere in the input, so we have to consider the entire input array. So we have 2 pointers. I call them the left and right pointer, but sometimes people will call it the low and the high pointer. Basically, it's our 2 boundaries. which make up our search space. So by taking our two boundaries and adding them together and then dividing that by 2, we can get approximately the middle. So in this case, that's going to be 0 plus 7 divided by 2, and usually we round down, so this is going to evaluate to 3. So this is what we call our middle index. I'm going to call it M for short. M is going to be at index 3. So taking a look at some pseudocode, this is what we've done so far. We've initialized our left pointer to 0, and we've initialized our right pointer to be the length of the array minus 1. And then we start looping. We calculate our mid pointer between the left and right pointer, dividing by 2. And then we want to check the value at the mid pointer. We know there's 3 cases. Either our target is greater than this value, meaning it's actually somewhere to the right, or our target is less than this value, meaning it's somewhere to the left. And the third case, which I've used as the else case, is we've found the target. Because if the target isn't greater and it's not less, then it must be equal. At that point, we're going to return mid, which is going to be the index. That's what we're trying to return, the index. So in this case, clearly our target 8 is greater than 4. So we know we should now start searching over here. So what should we do? Well, we have to update our search space to be over here. How do we do that? Well, our right pointer is already where it should be. So the only thing we have to do is take the left pointer and shift it over here. And how am I going to do that? Well, I'm just going to take mid plus 1, because we know this is not the solution. And we know that everything to the left of it is also not going to be the target because the input is in sorted order. We can only assume that because this is sorted. So we're going to eliminate all of these from consideration. And now we're going to go back up to our loop, and let's just assume that this mid is going to be changed now as well. So this is the case that we ended up executing. Target was greater, so we updated the left pointer. And actually, to make things a little bit more interesting, I'm going to change the target. Instead of being 8, I'm going to change it to be 5. So let's assume our target is 5. An initial part of the code would have executed the same regardless of whether it was 8 or 5, because 5 is also, greater than 4. We would have still executed that. But continuing, we're going to now calculate mid again because our loop is going to execute. I'll touch on this condition a little bit later on, but our mid now is going to be 4 plus 7 divided by 2. That's 11 divided by 2. We know we round down, so we're going to get 5 as our mid. So let's put mid over here at index 5. Now let's compare 6 to our target. Is our target greater than 6? Is 5 greater than 6? Nope, so we don't execute that. Is our target less than 6? Yeah, our target is less than 6. 5 is less than 6. So now we're going to execute this portion of the code. So now what we would logically want to do at this point is, since our target is not 6 and it's less than 6, we know it's going to be somewhere to the left. So would that mean it's somewhere over here? Well, we already eliminated all of these from consideration. So yeah, it's somewhere to the left, but it's not anywhere beyond this point. So how we're going to handle that is by taking our right pointer and moving it to be at mid minus 1. It's to the left of mid, so this is where our right pointer is going to go, and you can see our left pointer is also at that position. What that means is our search space was reduced to a single value. That's good because that means we're either close to finding our result or our result doesn't exist in the input. By the way, if we're searching to the left, that means we removed all of these from consideration. So now finally, we're going to execute the loop one more time. We're going to calculate our mid. Left and right are both 4. So we're going to say 4 plus 4 divided by 2. That's of course going to be 4. And that makes sense because this is the only position in our search space. So now we're going to check, is our target greater than 5? Nope. Is our target less than 5? Nope. That means the else is going to execute. That means our target, which is not greater than 5 or less than 5, must be equal to 5. So therefore, we found the solution. We can return the index mid, which is 4, so we return 4. We found the solution. Now, it's possible we would not have found a solution. Let's look at a slightly different example. Let's say our target was actually 9. We would have still gotten to this point. Our mid would have been over here, and we would have executed the loop again. Is our target greater than mid, which is 6? Yes, it is. So then we're going to execute this portion. We want to then search to the right. If our target is greater than 6, it must be somewhere over here. So we update our pointer left to be over here, and we remove these from our search space. So next we're going to execute the loop again, and the condition, by the way, for us continuing to execute the loop is if our left pointer is less than or equal to our right pointer. That basically means we have some existent search space that we're searching over. Even if left and right are equal, that means we have one element remaining. And if left is less than right, that means we have multiple elements remaining for us to search over. So now we calculate mid again. 6 plus 7 divided by 2 rounded down is going to be 6. We're going to check, is our target greater than 7? Yes, it is. And this is where our mid was, so we're going to take left and set it to mid plus 1, which is going to be over here. So we remove this from our search space. Our left pointer is over here as well. Now we check, are we executing the loop again? Well, left and right are equal, therefore left is less than or equal to right. We calculate mid again. It's going to be 7 plus 7 divided by 2. That's, of course, 7. So this is where our mid is going to be. Now, is our target greater than the value here? Yes, it is once again. So what are we going to do? The algorithm is going to say set left equal to mid plus 1. So now left is going to be over here. So basically, it's gone out of bounds. And then we try to execute the loop again, but at this point, left is definitely not less than or equal to right. And by the way, our search space is empty. So this is always going to execute. Left is not going to be less than or equal to right anymore after our search space is empty. And that means we did not find the target that we were looking for, so we're going to end up returning -1. This would have executed the exact same way if instead of our target being too large was actually too small. So maybe it's 0. We would have crossed all of these out, and our left pointer would have been here, and our right pointer would have gone right over here. Or what would have happened maybe if our target was actually equal to 2? It's not too small and it's not too big, it just doesn't happen to exist in this range. Well, to quickly simulate, first we would check mid. It's not the target. We would cross all these out. Our target must be somewhere over here. So among these, we approximate the middle. We check, is this equal to the target? No, the target is too small, so it's not this or this. Then our right pointer would be over here. And we would check, is this equal to 2? No, our target is greater than this value. So then we would take our left pointer and then move it to the right by 1. And then at this point, we would say, well, our left pointer is not less than or equal to the right pointer, and we don't have any elements remaining to search, so we return -1. That's the general simulation. That's the idea behind binary search. It can seem complicated at first, but once you get used to it, it's not too bad. But what about the time complexity? Why do we care about binary search at all? We could just scan through the input and find the target in O of n time. Isn't that good enough? Well, with binary search, with every iteration of the loop, we are eliminating at least half of the search space with one execution of the loop. And then we eliminate half of the remaining values. And then we eliminate half of the remaining values again until we have a single value. And then we eliminate that as well. So what's the math formula for what we're doing here? When we eliminate half, aren't we taking the length of the input? Let's say the length is n, and we're dividing it by 2 again and again and again until it's equal to 1. We talked about that earlier with merge sort. How many times can we divide a value by 2 until it's equal to 1? Because that's going to tell us how many times this loop executes. Well, we talked about it earlier. The formula for that is actually log base 2 of n, and usually we don't even mention the base 2, so this is log n. That's the time complexity of binary search. That's how many times the while loop is going to execute. Inside the while loop, we're just doing a constant time operation, so we don't care too much about that. But this is the worst case runtime, and we know log n is much, much more efficient than big O of n. And in terms of memory complexity, we're just allocating a few pointers. We're not allocating any additional data structures or arrays or anything of variable length. So the memory complexity is big O of 1.